Hi, in today's video we're going to be looking at the first stage in designing a new GPS disciplined oscillator. Now if you're a subscriber right from the beginning, you'll know that I did actually rescue a unit off eBay, modified it for my purposes, and we had a 10 MHz reference with a nice clock and everything on the front of the unit. Unfortunately, it no longer seems to want to work, so it doesn't want to find any satellites, and also the unit wasn't really telling the time and date properly, so the epoch issue with the firmware was causing it to tell the incorrect time and date. So what I thought we'd do this year is design a new unit, something that you can build yourself as well. So it's going to be based around a U-Blox GPS module, so something a little bit more up to date and something that's a lot more configurable. Now in that unit, rather than just using a microcontroller, we are going to end up using some kind of FPGA type device, possibly one of these Lattice MachXO2 devices, which is technically a CPLD, but the FPGAs or CPLDs of this nature are excellent for the type of timing tasks that we're likely to be doing on the GPS disciplined oscillator. So there's a lot of advantages which I will go through in more detail when we get to the point where we're doing the actual GPS disciplined oscillator design. But what I thought we'd do today is just get familiar with the MachXO2 as a device. And to do that, we are going to need to have a front panel on the unit that is going to have the time and the date. And I thought what we'd do is build up this 7-segment clock PCB. So I've had this PCB made at PCBWay and they supplied it for this video, and they did a great job of getting this out in really quick time despite all the problems in China. So really quite happy with the quality of the board, everything looks absolutely fine. And what it is 3 double-digit 7-segment displays. We've got a couple of LEDs between them for the colons, and this is sort of a development board just so that I can do something a little bit more visual with the VHDL that we're going to write, just so that I can make sure that I'm doing something correct, because when we're on to the algorithms for designing the GPS disciplined oscillator, any problems are going to be a little bit harder to diagnose, and I just want to get familiar with the tools again because it's been a while since I've used them. So this just has some Darlington drivers for the common anodes, and then we've got a 3 to 8 line decoder, so that's a 74HC238, and then another Darlington driver, and then there's a P-channel MOSFET driving each of the digits. So very simple multiplexing scheme, and basically we're just going to try and do the timekeeping, the multiplexing and everything in some VHDL running on this device, and then we'll be able to feed in some clocks, so we can feed in the clock that does the 1-second updates, and also hopefully we'll be able to feed in the clock and adjust the scan rate so you can see how it's all working and we can make sure it's working properly. So what we're going to do now is just assemble up the board quickly, and then we'll get on with the actual VHDL. So there's nothing too complex on the PCB itself. These SOIC packages are about as fine pitched as anything else on the board, and unlike some of the finer pitched devices, these ones can pretty much be soldered a pin at a time rather than needing to do any drag soldering. So the first thing that we're going to do is just put a little bit of solder on one of the pads in the corner, and then we can position the device and just tack that corner in place. So once you're happy with the positioning, just tack down another corner, and then you're free to go about soldering each of the individual pins. So here's our completed board. I think that looks pretty tidy. I've put a pin header along here so we can hook it up to the development board. So we've got some jumper wires here. These are just the female 0.1-inch header type connectors, and that will just plug straight into the pin header on this board. Now one note about this development board is this is exactly how development boards should be designed. There's no crap on here that you're not going to use. Things like the Microchip Explorer board is a really good example of how not to design a development board, because it's filled with so much stuff you can't actually design your own application around it because all of the pins are tied up with peripherals already on the board. This one just has some supporting hardware, so this actually has the JTAG interface on the board. It can program the device just through the USB interface, and it also gets the power from there, and then just all of the pins are brought out onto pin headers, apart from these 8 that just go off onto 8 LEDs. So this is like absolutely spot on for this type of work where you just want to get something up and running. You can daisy chain it to a whole ton of other boards They've done a really good job on this. So if you're thinking about having to play with some FPGA type devices, I definitely recommend this as a board because you can just hook it up to whatever you want and you haven't got any nonsense to mess around with. So let's have a little look at the software. Right, so here we are in Lattice Diamond, which is a free IDE which is available on the Lattice website, and it's completely free to use for the MachXO2 devices. I think for some of the more exotic parts there are licensing options available, but it's completely free for our purposes, and all you need to do is go to File, New, Project, and in that you can choose which device you're using, and then if you've already got some source code you can include it in there, or you can simply just create a new code. So I've created a new file, a new VHDL file called main_statemachine.vhd, and there's basically two tasks that we want to perform on this board. So we've got our timekeeping task, and then we've got our display multiplexing task. So let's have a little look at how we design a multiplexing display driver. So the first thing we need to do is create the state machine that's going to do the multiplexing. So there's 7 different states, there's 6 digits plus the colons, and in each state we're going to display the bitmap data to display the digit on each individual digit. So first of all, we are creating 2 signals called present state and next state, and those are of type state type, where we've actually got 8 different states here, but we only need to use 7 of them. And then a little bit further down is where the state machine actually is. So you can see here that we've got the process. The only item in the sensitivity list is the refresh clock, which is a clock signal which indicates when to move on to the next digit. And so every time that clock sees a rising edge, then we move on to the next state. So you can see here, for example, when it's in state 0, the input to the multiplexer on the display is 000, which corresponds to the first digit on the display. And then we actually send out the data on the parallel bus to be displayed on that digit. Then we move to the next state, and then the next time that we see a rising edge on refresh_clock, we then enter here again and do the next state, and so on. So we just keep going through here, and the timing is controlled by the frequency of refresh clock. Now you'll see here that we're actually assigning values to the same signal called digit data, but the actual numbers that we've got in hours 10/, hours 1/, for example, are all BCD numbers, so just a number from 0 to 9. And what we actually want to display on the display is some numbers that we can read. We don't want to send out a binary value, we actually want to send out numbers. So further down in the code we've got a process with only digit data in the sensitivity list. That means that every time it sees a change occurring in digit_data, then it starts this process. And here's the lookup table part. So it's whenever the input is 0, for example, then it looks up what the bitmap value is, which is all of the segments apart from segment G, and it feeds that into segment_data_latch. For a 1, then only segments B and C are illuminated, and so on. So this is a really simple way of creating some ROM, and it means that you can create custom characters and that kind of thing, and do it very quickly. You can either latch it in, clock it in, or you can do it as combinatorial logic. So depending on your application, this is highly configurable. The next part is actually creating the clock, and for that we need 2 synchronized clock signals. You can do it with just one and then divide it down later on in the VHDL, but basically we've got a 2 Hz clock and a 1 Hz clock. So the 1 Hz is obviously used for the timekeeping. The 2 Hz is done so that we have some flashing colons between the digits. And here is our 24-hour clock process. So second_clock is in the sensitivity list. That just means that every time we see something happening on second clock, then we start this process. And it's looking for the rising edge of that clock signal. And then simply we've just got some code here which does the processing of the numbers. So each time we come in here, we increment the seconds. If the seconds ends up equaling 9, then the next time round what we're doing is just assigning it back to 0, and we increment the tens and so on. And then at 24 hours I've done a complete reset, so if there's any weird kind of latch up that could ever occur, which it shouldn't do, then it just resets everything back to 0 at the stroke of midnight. And that's it. Again, This just runs completely independently. There's a bit of logic that's processing this, and then it's just feeding the numbers into these signals here. So hours ones count, hours tens count, and so on. It's pretty straightforward to do. And now we should have a system where we've got a multiplex display counting time. The next thing to do, and you might want to do this quite periodically, is obviously to save the VHDL. And when you do this, it goes through and checks for errors. And you can see here we've got 0 errors and 0 warnings. So the next stage is to actually synthesize the design, and this is where it turns it into actual compiled code effectively. So you synthesize the design, it goes through, checks everything is all right, and you also get all of your timing data here. So you've got a timing report summary, and this gives you an indication of the maximum speed at which various parts of the VHDL can run. At this point, we now want to assign the inputs and outputs actually for physical pins on the device. So if we have a look here, in the entity for 7-segment display, we've got some inputs and outputs that are going to go out to our display board. And we want to actually assign some pins on it. So here we can go to the spreadsheet view, and this is where you can select which pins to use. So you can see here, for the multiplexer pins, I've picked 38, 39, 40. The outputs to the segments from 49 all the way up to 56. There's a couple of pins missing because there's power pins in between those. And then we've got 2 inputs here, refresh clock and timekeeping clock. And those are going to come from a signal generator to start with, so that we can see the multiplexing and the timekeeping in action. We can also select all of the other options associated with input and output pins. So for example, we can choose the logic voltage type. So the default's 2.5 volt logic, but there's 1.2, 1.5, 1.8, 3.3 for example. So we can pick any of those for the inputs and outputs that we want. We can choose whether it's got pull up or pull down resistors, whether it's open drain, and everything else that you might want to select in relation to inputs and outputs on the device. You can also have a look at the schematic of the netlist it's come up with. So we click on Netlist Analyzer, and then we can see the actual schematic, and this can be really useful for debugging your design. Now there is actually another tool that is included with it, and this is called Simplify Pro, and if you load this up, this is a more dedicated tool, and then we should be able to run the synthesis, and then we can go through and actually have a look at the logic again. So we can go through to the RTL, have a look at the flattened view for example, and this is where all of the logic exists. So if we zoom in, you can see literally at gate level how it's implemented that HDL. So for example, we've got a latch here that's being clocked by the signal coming in here, and you can trace it through and see what else is driven by that clock signal. If we go through to the end, for example, we've got our ROM that we created. So this is where we feed in a 8-bit value, and it displays the bitmap of the number that we fed in. And then if we actually click on the name of it, you can see where it's inferred that in the VHDL. So you can really debug your code, have a look at what it's done, and if you need to, you can go through and optimize it. The other thing that you'll almost certainly want to do on your design is simulate it, but I'm going to cover this in another video when we do some more in-depth stuff on the FPGA. But it's safe to say that they do include active HDL by Aldec in a version that is specifically for Lattice Diamond. So I think it is slowed down. You can pay for a much faster version, but for general purpose use, this one's absolutely fine. But as I said, I'll cover this in another video in the future. So assuming that we've got our code all correct, what we actually want to do now is actually program our FPGA. So we're going to go through, we've already synthesized the design. We then want to map the design. We'll just make sure it's all saved. And at this point, this is where it's used all of these pin assignments and created our various files. We can then place and route the whole design. And then finally, we can create our programming file, which is the JDEC file. Once that's done, we can actually program the device. So I've got the board connected up now. It's already detected the LCMXO2 7000HE. Then we just click program. And the result of programming up the FPGA is that we've now got a fully functional clock. So here you can see that it's keeping time, it's doing the multiplexing on the display and flashing the colons on and off. Now because we've got the clock signals being fed in externally, we can actually control those so we can see a little bit more what's going on. Now obviously in a final implementation, if we were just designing a clock on its own, we could use a crystal and divide it down into some VHDL very easily, and it would just keep time and do the rest itself. But we can feed these in with clock signals, and I've got it hooked up to the signal generator at the moment. But part of the reason that I thought about doing this video is I'm sure many of you watch Martin Lawton. He's working on a extremely accurate clock for his lab that isn't internet connected or connected to a GPS or anything like that. And he's been playing around with a whole load of different clock solutions, mostly based around firmware, microcontroller based clocks. And he's faced some issues with that. I think he's wasted a little bit of time with one of the Chinese clocks that seemed to have a lot of jitter. I think there was a firmware error on that one. But using a hardware solution like this is completely deterministic in terms of the timing. So that's the very nice thing about using an FPGA, is that you get your timing analysis. You can use Simplify Pro to have a look at all of the timings, and you'll know that your device, from feeding a clock signal in, will have the output updated in a given period of time, and that will be guaranteed based on the hardware implementation. With the firmware, if we were keeping time, it could be busy doing something else before it's got a chance to go to a particular interrupt routine or something where it's incrementing the time. And, he's measuring the output of the display on the oscilloscope, and that is not necessarily a guaranteed output, where the clock is actually incrementing. So something like this will give you a much more deterministic output on your display. So we've got the clock signals hooked up to the signal generator. We can actually decrease the clock rate of the refresh rate. So if we start changing that, you can see it starting to ripple there. And then we're doing one complete refresh per second. So you can see it scanning across, and then it goes to the colons as the final step, and then starts back again at the hours. Now the other thing we can do obviously is change the clock speed for the timekeeping. So we've got our signal coming in at the moment. If we start speeding that up, then obviously we're able to increase the rate at which the clock starts counting. Now theoretically, based on the timing analysis, this should be good for several megahertz. So here we are at 10 megahertz and it's still working properly. 20 megahertz, and it's going as high as this signal generator will go, and it's still keeping time. So that just shows that this is absolutely ideal for anything where we've got some high speed signals coming in. In the case of our GPS disciplined oscillator, we're going to want to control a 10 megahertz ovenized oscillator, and this can be fed in and processed with still a lot of overhead. The clock speed of this Lattice FPGA, I think on this type, is up to 240 megahertz, so we can have clock speeds way in excess of the clock of the ovenized oscillator that we're trying to control. Now there is a book that I can recommend. It's VHDL for Engineers by Kenneth Short, and the nice thing about this book, which I did have to refer to quickly when I was setting up this design, is it's specifically designed for engineers who are likely to be implementing VHDL on an FPGA. Now VHDL does have uses outside of FPGA work, and the difference is that some code that you can compile doesn't convert into synthesizable logic that you can run on FPGA. So this one has some really good information on the distinction between those, and I think this book is particularly good for university students who are just starting out. It seems to have everything that you'd need to know in here, so a really good book. I'll put a link to it down below. It's not an affiliate link or anything like that, it's just a personal recommendation from me. I do think this is a really good book. So if you've got any thoughts or comments, don't forget to leave them in the comments section down below. I think this should be quite a fun and interesting project, just because we're doing something a little bit different from what we normally see. Now, we have got some other videos coming up soon. We've got some PCBs coming. Full production is pretty much back up and running in China now, so we've got all of the other designs. We've got the big clock, which is being produced. We've got a smaller version, which is actually on its way now, and a couple of other boards, so we've got some interesting projects coming up. We've also got some reviews of some new items to have a look at, and they'll be coming up soon. So I hope you enjoyed the video, found it interesting, and until next time, thanks for watching.